Hello everyone, I am Dr. Rafiq Ahmad. Today I am going to deliver a lecture on the topic coordination complex ordination compound. Let us start the coordination complex or coordination compound with a basic concept, that is addition compounds. Addition compounds are those which involve the combination of two or more salts in a stoichiometric ratio. For example, if I am taking the salt A and I am combining it with the salt B, but we have to make aqueous solution of salt A. This salt A should be in the aqueous form. Aqueous solution should be there. Aqueous solution. And salt B should be also in aqueous solution. That is aqueous solution of salt B. Then we are combining these two salts. Salt A, aqueous solution of salt A, and aqueous solution of salt B. Then we are heating it for the crystallization, so that the minimum amount of solvent will be there, and that will lead to the formation of the crystal type of compounds, and those type of compounds are called as addition compounds. So addition compounds are the combination of two salts in a stoichiometric ratio. Suppose salt A in the aqueous solution of salt A combined with the aqueous solution of salt B. Then we are heating it for the crystallization, so that minimum water quantity will be there, or less quantity, the water quantity will get evaporated, and after water quantity will get evaporated, there is a formation of crystals, and those crystals are the addition compounds. These addition compounds are of two types. Two types of addition compounds are. One is called as a double salt, another is called as a complex salt. We can also call it as a coordination complex. Double salts includes more salt, potassium alum, and chloride. These are the examples of double salt. Now we have to fix today's our chapter. It belongs to the coordination complex or coordination compounds or coordination complex salts. What are coordination complex or coordination compounds? Coordination compounds are those in which the metal atom or ion is linked to the ligand through coordinate bond, and those compounds where the metal cation or atom is linked to the ligand through a coordinate bond, and those compounds are called as a coordination complex or coordination compounds. Coordination complex or coordination compounds are represented by the general formula MLN raised power X. This M is a metal and X is the charge on the complex, L is the ligand, and N is the number of the ligands. Let us represent general one example with one example. For example, I am taking one example here, that is K4FeCN6. This is a coordination complex or coordination compound. This K4, which is outside this bracket, and this is called as ionization sphere or counter ion. This K4, which is outside this bracket spheres, this is called as a coordination sphere or ionization sphere. And this iron belongs to the metal, and Cn is called as a ligand. Cn is represented by the ligand. This Cn is a ligand, and this number represents the coordination number. This 6 represents the coordination number. And the species which is inside the brackets, these two brackets, this is called as a coordination sphere. The sphere in which metal cation is linked to the ligands, this is called as a coordination sphere. So, coming to the next point, that is complex ion. Complex ion is a species in which the metal is coordinated to ligand through coordinate bond. This was the general representation of the coordination complex or coordination compound. Here I talked about the coordinate bond or dative bond, which is present between the metal cation and the ligand. This coordinate bond or dative bond, it's also called as a dative bond. It is a type of bond that is formed by the electrons, but those electrons are shared by only one atom. Suppose if I am taking the example here, that is NH3. I am taking the example, I have already taken the example, NH3. This NH3 has a lone pair, and this NH3 donates its lone pair to this metal, leading the formation of a bond. This bond, which is formed between this ammonia molecule and the metal ion, is called as a coordinate bond, because in this bond the electrons are donated only by the ammonia molecule. So whenever there is a bond formation, and that bond formation involves the lone pair or the electrons, but those electrons are shared by only one molecule or atom, that bond is called as a coordinate bond or covalent bond. So I have shown here, this is the coordinate bond or covalent bond. This was about the coordinate bond or covalent bond. Now moving to the types of coordination complex. Coordinates are two types of coordination complex are there. One is called as a neutral coordination complex, and another is called as ionic coordination complex. These ionic coordination complexes are further divided into cationic coordination complexes and ionic coordination complexes, and another includes the cationic ionic coordination complex. The types of coordination complex, it is categorized on the basis of charge on the complex. For example, if I talk about this charge, I am taking the one example, CONH3 whole 6. This X represents the charge on the complex. If there is no charge, if the value of X is equal to 0, that means the complex has a zero charge, that is no charge. Then those complexes are called as a neutral complex. For example, I have given one example here, CONH3 whole 6. There is no charge on the complex, so we can say that this complex is a coordination complex, a neutral complex. Okay. Now moving to the ionic. I told ionic, these are two types. One is cationic and anionic. Anionic coordination complexes are when there is the negative charge on the complex. For example, I have taken the one example here, K4FeCN whole 6. This is actually represented here, this like this. That is 4K positive gets dissociated. That is 4K positive, and FeCN whole 6 is 4 negative. Or in this complex, there is a negative charge. So this negative charge represents that this complex belongs to the anionic coordination complex. That is anionic coordination complex. Coordination complex. Okay, because of the negative charge on the complex. Now, here is one more example for the cationic coordination complex. If on the complex there is the positive charge on the complex, then that complex is called as a cationic coordination complex. Look at this example, CONH3 whole 6 Cl3. It will be represented like this: CONH3 whole 6 3 positive plus 3 negative. Here on the complex there is a positive charge. There is a positive charge. So whenever any coordination complex has the overall charge on the complex is a positive, and that coordination complex is called as a cationic coordination complex, and this is called as cationic coordination complex. Okay, now moving to the cationic and anionic complex, what it represents actually. Cationic anionic complexes, coordination complexes involve that where both, so their type of complexes which involves both cationic will be also there and anionic will be also there. For example, I have taken one example here. This is the cationic anionic coordination complex, CONH3 whole 6 and FeCN whole 6. This may be also actually the compound looks like this. CONH3 whole 6 the positive and FeCN whole 6 the negative. Actually there is a bond between these two complexes. That bond is ionic bond. Ionic bond. So whenever there is a complex that involves both cationic complex and anionic complex, that complex is called as a cationic anionic coordination complex. This was about the types of coordination complex. Now I have already discussed the additional compounds are of two types. One was double salts and another was the complex salt or coordination complex. Now we can differentiate here double salts and complex salt. But actually this, because these double salts and a complex salt, as per the exams pattern, the question is being asked in the competitive exams as well. Now we will differentiate here what double salts or complex salts are. Double salts includes they get completely dissociated into ions. What it means, when we are taking, for example, we are taking one double salt and we are dissolving it in a water, making its aqueous solution. After making aqueous solution, they get dissociated into its ions, into those ions by which it is formed. For example, I have taken here the example potassium alum. Potassium alum is a double salt. When we have making the aqueous solution of this Mohr salt, it gets dissociated into Fe positive plus 2 times of ammonia and NH4 positive, plus 2 times of SO4 positive, and 6 times of water. So I mean to say, whenever we are making the aqueous solution of double salt, that double salt gets dissociated into its ions. Example I have shown here, Mohr salt. But complex salts has a one, they do not get completely dissociated. For example, I have taken the one example here, K4FeCl ka whole 6. This is a coordination complex. It does not get completely dissociated into ions. It only partially dissociation is there. That way it leads the formation of 4K positive and FeCl ka whole 6 is 4 negative. So whenever we are making the aqueous solution of complex salt, they get partially dissociated, which I have shown here, K4FeCl ka whole 6. It gets dissociated into 4K positive plus FeCl ka whole 6 is 4 negative. Okay, this is the first difference. Now moving to the next difference between double salt and complex salt. Double salts lose their identity in aqueous solution. That means when we are making the aqueous solution of the double salt, they lose their identity in aqueous solution. What it means? For example, if I am taking the example, I have a, for example, there is a company. Company name is OX is the company name. And this company name has a 4 individuals, A, B, C, and D. These 4 individuals have made this company. They are the owners of this company. So in this company, A, B, C, D belongs to the OX company. But due to some reasons, this company got breaks. Yani A got separated into A, and B got separated into B, and C got separated, and D got also separated. So after separation, we cannot call it as a OX company. Why? This OX company was the sum group of A, B, C, and D. But after breaking of this company, there is an individual A, B, C, and D. So that is why I am saying that they lose their individual and they lose their identity in aqueous solution. That means after dissolving of the salt and double salt in aqueous solution, the double salt gets completely dissociated. Here is the same case. If I will talk about the company name now, after dissolving this, there will be no name. There will be the individual names A, B, C, and D. Now moving to the complex salt do not lose their identity. Why? Because if the K4 potassium gets separated, but there is another complex which involves the 2 molecules, which involves the 2 iron and cyanide. So if, for example, this K4FeCl ka whole 6 is a company's name, for example, AL is the company's name, but if after this K potassium gets separated, but this company is already there because only one gets separated. These two, iron and cyanide, is already there. They have a company name. So that is why we are saying they do not lose their identity. That is, only potassium gets separated, but iron and cyanide is already there and their company name is already here. So I mean to say that they do not lose their identity. Okay. Now moving to the next difference, that each ion will give the positive test. If I will, for example, if there is an aqueous solution where A is there, B is there, C is there and D is there, they will give these four ions are already in aqueous solution. And if we will test for A will give the positive test. If I will test for B is give the positive because they are already there. If I will go for the test for C will give positive test. If I will go for the test of D, and D will give the positive test because they are in the solution. But if I will go for the test of OX company, they will give the negative test because this company has already been broken down. Okay? But moving to the complex salts, individual ions lose their identity, individual ions lose their identity. That is, each ion will not give positive test. Why? Each ion will not give positive test. For example, if K4 gets separated here, and after test K4 will give, potassium will give the positive test. But in the aqueous solution of this complex salt, potassium is there and this complex ion is there. If I will test for the iron, iron will not show the positive test. Why? Because this iron and cyanide. If I will go for the test of cyanide, it will not show the positive test because they are in the form of complex ion. So they are losing their identity, iron and cyanide, in the form of complex ion. But potassium has given it just a positive test, that means potassium is there. Potassium is in the aqueous solution. Okay. This was all about the difference between the double salts and complex salt. Now moving to the next concept, that is the types ligands. What actually ligand is? Now moving to the next concept, that is ligand. Ligand, what ligand actually is? Ligand is a ion, molecule or that atom that has one or more than one lone pair of electrons and share those lone pair of electrons to a metal cation to form a bond called as a coordinate bond. So ligands are only the species. Remember, ligands are the species, ions includes molecules that have one or more than one lone pair of electrons and they can donate those lone pair of electrons to the metal cation or metal atom or ion to form a coordinate bond, and that species is called as a ligand. For example, I will give you a few examples here. This is the ammonia molecule. Ammonia molecule has a lone pair of electrons. Water molecule, lone pair of electrons. Cl negative is have the lone pair of electrons. F negative is a lone pair of electrons. So whenever there is a species that have a lone pair of electrons and that can donate that lone pair of electrons to the metal cation and lead to the formation of coordinate bond, those species are called as ligands. I have shown few examples here. Ammonia is a one lone pair, then water molecule, then Cl negative and F negative, all includes the category of the ligands. Okay. Now there are different types of ligands. Depends upon the number of lone pairs and number of donor atoms. Ligands are classified into monodentate ligands, bidentate ligands, tridentate ligands, tetradentate ligands, pentadentate ligands, and hexadentate ligands. Firstly, I have one more thing you need to remember. This ligand donates its lone pair of electrons to the metal cation or metal atom. That species that donates lone pair of electrons, they act as a Lewis base. So we can say the ligand which donates its lone pair of electrons to the metal cation, they act as a Lewis base. And the species that accepts the lone pair of electrons from this ammonia molecule, that is metal, they act as a Lewis acid. So, what is Lewis acid? What is Lewis base? Lewis acid is that species that accepts the lone pair of electrons. Here, metal accepts the lone pair of electrons from the ligand and act as a Lewis acid, while as ammonia molecule donates a lone pair of electron to the metal cation and act as a Lewis base. This concept. Remember this type of concept, that ammonia, that ligand act as a Lewis base, whereas the metal cation act as a Lewis acid. Now moving to the types of the ligands, monodentate ligands. Monodentate ligands are those types of ligands that has one lone pair of electron or one donor atom and can coordinate with a metal cation through that lone pair or through that donor atom and leads the formation of a coordinate bond or dative bond. Those ligands are called as a monodentate ligands. So monodentate, you need to remember, these are the species, that is ion or a molecule having either one lone pair of electron or one donor atom, and that donates that lone pair to the metal cation to lead the formation of a coordinate bond. That atom or that ion or molecule species is called as a monodentate ligands. Monodentate ligands examples includes ammonia molecule, water molecule, F negative, Cl negative, I negative, Cn negative, CH3CO negative, NO3 negative. There are different examples of monodentate ligands, but I have shown here few examples. They act as a monodentate ligand. That is, they have one donor atom or one lone pair, and by that lone pair, they form the one coordinate bond with a metal cation. Okay, this is called a monodentate ligand. Now moving to the second type of ligands, that is bidentate ligands. Bidentate ligands are those types of ligands which has two lone pair of atoms and have two donor atoms, either two lone pair of electrons and have two donor atoms, that is two donor atoms, and can coordinate with the same metal and leads the formation of a coordinate bond. Those ligands are called as a bidentate ligands. What are bidentate ligands? Bidentate ligands are those ligands which have two donor atoms and can coordinate with the metal cation through those two donor atoms and leads the formation of a two coordinate bonds with the same metal, Those ligands are called as a bidentate ligands. Example I have shown in oxalate. This is the one example, oxalate. This is called as oxalate. CO negative and CO negative. It's a bidentate ligands. And the second is the glycinative. And this 1,2-diamonoethane is also a bidentate ligand because there's two donor atoms, nitrogen, ammonia molecule. Here this is, and another example is 1,2-diaminopropane. 1,2-diaminopropane. This is also a bidentate ligand because it has two donor atoms and can coordinate with the metal through these two donor atoms. So remember this one more point. This 1,3,12, that is 1,2-diaminopropane. This is the only ligand that is the chiral ligand. Remember, this question may be asked in the competitive exams. Name the bidentate ligand which acts as a chiral ligand. Your answer should be 1,2-diaminopropane. 1,2-diaminopropane is a chiral. Okay. Now moving to the next type of ligands, that is tridentate ligands. Tridentate ligands are those ligands which have three donor atoms and can coordinate or three lone pair of electrons, or more than lone pair can be more, but we can remember there are three donors or three donor atoms and can coordinate with a metal with those three donor atoms, leading the formation of three coordinate bonds with the same metal. For example, I have taken the example here. This is the example that is this is one example. This is called diethylene triamine. Diethylene triamine is one example. It has three donor atoms. One is this nitrogen, another is this nitrogen, also lone pair. This nitrogen also lone pair. So it has three donor atoms and it acts as a trident ligand. Another example is ethane ethane monoacetate. This is monodentate, this is tridentate. This is another example of tridentate, that is it has three donor atoms. One includes this nitrogen, another is this nitrogen, and one acetate group is here. This also acts as a donor atom, that is O negative, also acts as a donor atom. So 1, 2 and 3. So we can say this is a tridentate ligand. This is also a tridentate ligand. Now move to another example, that is 2 terpyridine. This is also a tridentate ligand. It has three donor atoms, one nitrogen, this one and this one. So it has three donor atoms, so it belongs to the company of tridentate ligands. Okay, these were few examples of tridentate. There are so many examples of tridentate, monodentate, bidentate, tridentate, but I have shown here few examples. Okay, now moving to the next type, that is tetradentate ligands. Tetradentate ligands are those which has four donor atoms and can coordinate with a metal cation through these four donor atoms and lead to the formation of four coordinate bond, but that metal should be same metal. Example, NTA, natrilyl tetraacetate. It has four donor atoms. One is this nitrogen, another this acetate negative oxygen ion, another acetate group this oxygen ion, this another acetate group oxygen ion. 1, 2, 3 and 4. So this natrilyl tetraacetate has a four donor atoms and acts as a tetradentate ligand. Now another example is ethylene diamino diacetate. Ethylene. Another example is ethylene diamino diacetate. It also belongs to tetradentate ligands. How? Look, this ammonia molecule, nitrogen molecule is one lone pair, includes one. This nitrogen molecule is another, two, and this acetate group also acts as a ligand, has a negative charge on oxygen, and this acetate group also has a negative charge on oxygen, and 1, 2, 3 and 4. That means this diacetate, that is ethane diamino diacetate, also belongs to the tetradentate ligand. Okay, these were examples of tetradentate ligand. Now moving to the pentadentate ligand. Pentadentate ligands are those ligands which have 5 donor atoms and can coordinate with the metal, same metal, with those 5 donor atoms and lead to the formation of 5 coordinate bond or dative bonds. Example is ethane diamino triacetate. Ethane diamino triacetate. This is the one nitrogen lone pair. This one, and this is the second one, second donor atom. This acetate group also includes one donor atom. This acetate group also includes one donor atom, and this acetate group, this one, also includes another donor atom. So 1, 2, 3, 4 and 5. So this ethane diamino triacetate, also includes have a 5 donor atoms and includes in the pentadentate ligands. So pentadentate ligands are those ligands which have 5 donor atoms or 5 donor atoms and can coordinate with the metal, same metal, and lead to the formation of 5 coordinate bonds. Those ligands are called as a pentadentate ligand. Example is ethylene diamino triacetate. Now moving to the another type of ligand, that is hexadentate ligands. Hexadentate ligands are those ligands which have 6 donor atoms and can coordinate with a metal cation through those 6 donor atoms and lead the formation of 6 coordinate bonds are called as a hexadentate ligand. Those ligands are called as a hexadentate ligands. Example is ethylene diamino tetraacetate. Tetraacetate. That is 4 acetate groups are there. 1, 2. This is the second. This is the third one. This is the fourth one. And these 2 nitrogen atoms also included into the category of the donor atom. So 1, 2, 3, 4, 5, 6. So this ligand has a 6 donor atom and can coordinate with the ligand by these 6 donor atoms and lead the formation of 6 coordinate bond. So it will include in the company of the hexadentate ligand. Okay. Now moving to the another concept, I have shown here denticity. What actually denticity is? Denticity is simply how many number of donor atoms are present in a ligand, and that number of donor atoms will represent the denticity of the ligand. Denticity is nothing but a number of donor atoms in a ligand, and number of donor atoms in a ligand is called as a denticity. For example, if I will take the ammonia molecule. Ammonia molecule is a ligand. If this is a ligand, and in this ligand, how many donor atoms are there will represent its denticity. If ammonia molecule is here, this ammonia molecule has a 1 donor atom, that is nitrogen. That means we can say the denticity of this ammonia ligand has a 1. Denticity. Denticity of ammonia molecule is 1. For example, if another is, we will take one more example. Ethane, 1,2-diaminoethane. 1,2-diaminoethane. NH2, NH2. This is another ligand, ethane, 1,2-diaminoethane. This 1,2-diaminoethane has 2 donor atoms. One ammonia molecule and second is another ammonia molecule. We have now to see either ligands are same or different. We have only see how many donor atoms are there. Either they will be same or different. Here donor atoms are 2. One ammonia molecule, another ammonia molecule. So this ligand belongs to the has a denticity of 2 because this ligand has a 2 donor atoms. Both the donor atoms are ammonia molecule. So we can say this 1,2-diaminoethane has denticity of 2. Okay, this was about the denticity. Now coming to the next, one more important ligand, that is called as a flexidentate ligand. Question is being asked in the competitive exams, which among the following is a flexidentate ligand? Few examples are being there in the options, and you have to remember these examples. You have to thoroughly remember these examples which I have shown here. So first we will discuss what is flexidentate ligands. Flexidentate ligands are, they act as a both monodentate as well as bidentate ligands. These are the ligands which act as a both monodentate as well as bidentate ligands. Those ligands are called as a flexidentate ligands. Example: NO3 negative, SO3 is negative, SO4 is negative, CH3CO negative, CO3 is negative, NH2, CN, NC, N2, and O2. These ligands, whenever you will find these types of ligands, and your mind should strike that these ligands are the flexidentate ligands. Flexidentate ligands are those ligands which act as a both monodentate as well as bidentate ligands. Those ligands are called as a flexidentate ligand. Kindly remember these examples. The examples will be asked in the question in the competitive exams. Which among the following is a flexidentate ligand? You need to remember these examples. These molecules act as a flexidentate ligands. Okay. Now another concept is there, that is ambidentate ligands. What are ambidentate ligands? Ambidentate ligands are monodentate ligands. These are monodentate ligands that have 2 or more ligands in which there are 2 different donor atoms. And can coordinate to the metal through either of the donor atoms. So ambidentate ligands are monodentate ligands which have two different donor atoms. Two different donor atoms are there, but they can coordinate with a metal with only one of the donor atoms. For example, Hcn negative belongs to the ambidentate ligand. Here nitrogen can also act as a donor, sulfur can also act as a donor. Here NO2, this oxygen and this nitrogen also act as an oxygen may also act as a donor, and this nitrogen also act as may act as a donor. But it can coordinate with a metal, either nitrogen or with the oxygen. Here sulfur S2O3 is an example. S2O3 is negative, CO is negative, CN is negative, and SO3 is negative, 2 negative, and NH2 whole twice CO and NH2 whole twice CS. These are the examples of ambidentate ligands. This question may also be asked in the competitive exams, so you need to remember these examples. Remember these examples belongs to the ambidentate ligands. What are ambidentate ligands? These are monodentate ligands which have two different donor atoms. Two different donor atoms, but they can coordinate whenever they have to coordinate with a metal. They can coordinate either of the two different donors. They can they will not coordinate with the they will not coordinate by both donor atoms. No, they can coordinate with a metal through either one of them. Either, for example, if SCN is there, either they can coordinate with the sulfur or with the metal atom, or they can coordinate with the nitrogen to the metal atom. So these are the concept of the ambidentate ligands. These are the monodentate ligands which have two different donor atoms and can coordinate to the metal cation through either of the donor atoms. They are called as ambidentate ligands. Example these are the examples of monodentate ambidentate ligands. So you need to remember these examples. This was all about today's lecture. Actually, this coordination component is a vast chemistry. It may take a month, even 15 days to complete this topic. But this was my lecture was today. It was about the coordination compounds. What are the coordination compounds and additional compounds? What are the types of additional compounds? Two types of additional compounds. One was double salt, another was complex salt. Then I have defined what is complex salt or coordination complex. Then after definition of the coordination complex, we have represented the coordination complex where we have named coordination sphere, coordination number, ligand, metal cation, and ionization sphere. Then we move to the next step, that is coordinate bond or dative bond, where we have discussed what is dative bond or coordinate bond. And then we move to the types of coordination complexes. There are two types of neutral and ionic. Then ionic are also two types, that is cationic and cationic ionic complexes. And we have given the examples, different types of examples, while we can see which one is neutral and which one is ionic or which one is cation. Then we discussed about the double salts and complex salt, difference between the double salts and with the examples Morus salt, carnallite, and potassium alum. Then after that we move to the next concept, that is ligand, where we have discussed different types of ligands. What are ligands? What are different types of ligands? Monodentate, tridentate, hexadentate, all those types of ligands with examples. And also we have discussed with the denticity, what is denticity, and flexidentate, what are flexidentate ligands, what are ambidentate ligands. There was one more concept that I need to discuss about, but due to lack of the time, that was the calculation of the oxidation state of the complex and calculation of the oxidation number of the complex. Hopefully, if I got the time to discuss that, I will in the later stages. I will definitely discuss that. But due to the lack of the time, this was all about my lecture today. Thank you very much.